Hello, I'm Peter Bryzgalov. I'm a Chief Research Scientist at STAIR Laboratory of Chiba Institute of Technology in Japan. Thank you for your interest in our virtual poster presentation. Here is the title of our poster. The broad topic of this poster is training time of convolutional neural networks, CNNs. We are working on predicting training time of CNNs because training may require a lot of time and money, and to have an estimation of the training cost in advance would be extremely helpful. Unfortunately, however, we found that CNN training time can change extremely depending on the GPU type and training parameters. In this poster, we focus on one training parameter that has a particularly high impact on training time, the mini-batch size, to clarify how and why changes in the mini-batch size affect CNN training epoch time. To understand how epoch time changes with the mini-batch size, we measured the epoch time of a sample CNN VGG16 model on several NVIDIA GPUs. We observed extremely high variability of epoch times on all GPU models. For example, epoch time grows exponentially towards smaller mini-batch sizes, and on larger mini-batch sizes, epoch time gradually stops decreasing, around 200 and larger. Moreover, importantly, on some GPU types, we observed abrupt changes. Even a slight variation of the mini-batch size makes epoch time increase or decrease almost twofold. To understand why the abrupt changes happen, we investigated the underlying cuDNN library, which is used by many machine learning frameworks like TensorFlow, PyTorch, and Chainer. cuDNN provides several different algorithms for each convolution operation. cuDNN heuristically chooses one of the algorithms, depending on convolution parameters, memory requirements, and other factors. We do not elaborate here, but there is a short explanation of convolutional algorithms in cuDNN and convolutional layer shapes in the poster. To verify that changes of convolutional algorithms in cuDNN cause the abrupt changes in epoch time, we recorded convolution algorithms used by the sample CNN over a range of mini-batch sizes on all GPUs we used in the previous experiment, as shown in Figure 2. Then we simulated convolutional layers from VGG16 model with a benchmarking tool and estimated the epoch time for each layer. We show the estimation results in Figure 3. We can see that the shapes of aggregated epoch times of the simulated convolutional layers are very similar to the epoch times of the sample CNN. We could also reproduce the abrupt changes. Further, we can see that the abrupt changes correlate with the changes of algorithms used for filter gradient calculations. For example, change of algorithm from 1 to 3 causes a significant increase in the epoch time of the layer to 512 on the Quadro P2000 machine. In conclusion, we found that minor changes in the mini-batch size may cause abrupt changes in the CNN training epoch time. The cause of the abrupt changes is that underlying cuDNN library heuristics chooses different convolution algorithms depending on the mini-batch size. Because these algorithms may differ hugely in calculation time, using different algorithms may cause an abrupt change in the convolutional layer time. In the future, we plan to extend our research to other machine learning frameworks to consider cuDNN auto-tuning algorithm selection policy based on performance benchmarking. We also plan to consider other CNN models and datasets. Ultimately, we plan to design a performance model for predicting CNN epoch time on unseen mini-batch sizes and unseen GPU types. Thank you for watching our virtual poster presentation. If you're interested in more details, please check our poster PDF. If you have any questions, please feel free to contact us. Peter@stair.center